Hey everybody, Mr. Enyart here. Today we're going to be doing lesson 22 in Eureka Math for 6th grade, module 4, topic F. And we're going to be talking about exponents and using exponents in situations in real life. So how like folding paper is going to be our main one that really explains it. So stick around and I hope you enjoy. Let's do some math.
Mr. Enyart is here to help.
Let's go. Hey, so we're going to be talking about exponents, and a piece of paper is a great situation to help understand what exponents are. So an exponent is a new operation. It's different than addition, subtraction, multiplication, or division, but it does use multiplication as part of it. Multiplication is the combining of equal groups, but exponents is the combining of the equal groups that have been combined. Like, it's really confusing. However, this will simplify things. So let's say we're going to keep folding this in half, right? So right now, I haven't folded it in half at all, right? I haven't doubled it, if you will. How many pieces are there? Well, there's one. And this is why anything to the 0 power is 1. If I was going to fold it into 3 pieces, into thirds, or into sixths, or eighths, or whatever it is, and then keep doing that, that would be, let's say, multiplying it by that number over and over again. But if I do it 0 times, I still have my 1 piece of paper. So anything to the 0 power is 1. But let's go ahead and fold it 1 time in half. So now you can see I have 2 pieces, right? So 2 to the first power would be 2 pieces, right? So I'm taking it and folding it in half, and I'm gonna do that again. All right, so this would be, let's say, 2 times 1, all right, to the first power, even though you wouldn't do times 1, sorry, I shouldn't have said that. But I'm gonna fold it in half again. All right, so every time I'm folding it in half, I'm essentially multiplying that number that I had times 2. So I had 2 pieces, but now I have 4, and 2 times 2 is 4. Okay? So that would be 2 to the second power, right? So now, this is when I had 4 pieces, right? I'm going to fold this in half. I'm going to multiply it by 2 again. So this will be 2 to the third power. What do you think I'm going to have? Let's find out. All right, so now, right, I folded that in half. I had 4, but now I got 8, right? Because 4 times 2 is 8. Let's see if we can do that another time. So let's get back to where we were, right? This is when I had 2 to the third power, right? 2 times 2 is 4, times 2 is 8. All right, now we're going to do 2 to the fourth power. We're going to fold it in half again, all right? Try this. This paper is getting thick, kind of hard to fold. Ugh. Okay, so now I got this little thing. All right, so I had, I'm gonna bite it down, okay? So I had 8. How many do you think I'm gonna have now? Now I've got 16, 4 by 4. So again, I took that 8 that I had times 2 when I folded it in half. And so a folding piece of paper is a great way to see how powers of 2 work, right? If I had 2 to the 0 power, I don't fold it at all. Don't fold it in half at all. I still have my 1 piece of paper, so that's anything to the 0 power is 1. But once I do it in half once, so 2 to the first power is 2, because I have 2 pieces. Once I do that 3 times, right, I fold it in half once, and then I fold it in half a second time. So this is 2 to the second power, I had 4. When I did another one, that's 2 to the third power, I had 8. And when I did another one, I had 2 to the fourth power, which was 16. Now, theoretically, I can't keep folding paper over and over again. Eventually, it's going to get too hard. In fact, I think the thing is, once you've folded it 7 times, it's impossible to keep folding it or something like that. You can never fold more than 7 times, no matter how big the paper is. But each time, I'm multiplying what I had by 2. And so that would be powers, 2 as my base number to a specific number of powers. So let's put that into application with some other real life situations.
So here's a real-life application. Chemistry, all right, bacterial infection. I actually have a friend of mine, he's lives in Germany, and he's a pharmaceutical chemist, and he breaks down and tests out different pharmaceutical drugs like Tylenol and aspirin, and has to look at stuff like this a lot in a microscope, where you see that, let's say we have one cell, and you can read this on your own and pause it. But then that cell is going to turn into two cells. And every single cell, through each different life cycle, or let's say, I don't know, what do they call it in here? Fission, binary fission. But as it reproduces, so yeah, life cycle. As it reproduces, each one doubles itself. So we had 2 from the 1, but then those 2 each doubled themselves. So now we end up with 4. So this would be 2 to the 0 power. This would be 2 to the 1 power, there's 2. This would be to the 2nd power, there's 4. And then we get 2 to the 3rd power, there's 8. And then, of course, 2 to the 4th power, there's 16. So pause it, take a look, and see if you can kind of see what's happening. It might be easy to draw this stuff out, but we're looking for the quickest mathematical way to solve it. And, of course, that would be using exponents. So I'll let you fill this out because it's pretty straightforward, and it's just like what the video talked about with the folds and what that first page in your practice was that I didn't do because I did it by showing you the paper. But generation 1, which is 2 to the 1st power, was 2. Where did generation 1 come from? Generation 1 came from generation 0, right? Or the very beginning, generation 0. And of course, how many bacteria did that have? 1. So that means 2 to the 0 power is 1. And that would be in any situation. Let's say they were all, any kind, didn't necessarily double. Maybe it tripled or quadrupled every time, or maybe it was times 8 every time, right? Generation 0 would always still be 1. It would always have to start at 1. That's the beginning. So when you think of exponents, don't think of times 0 being 0, because you're not multiplying, right? You're not multiplying the base. Okay, this is what we call the base. We're not multiplying the base by the exponent, right? We're multiplying the base to itself, the exponent amount of times. So this is like the number of times to multiply the base number, right? So this would be 2 times 2 times 2. So this one I think is worth taking a minute to stop and think about. First of all, the volume of any three-dimensional rectangular object, rectangular prism, cube, is going to be length times width times height. So our length here is 3w, 3 times an unknown number. Our width in this case is w, width. Our height in this case is 2 times w. So I'm assuming that w here means the width. Whatever the width is, the length is 3 times the width, and the height is 2 times the width. So what we're going to do is, if we were to give w, or the width, centimeters, 1, what would be our volume? And you can see that what they did is they wrote the length, the width, and the height. And by multiplying, remember, in multiplication, you can do it in any order, right? So I'm going to be multiplying 3w times 2w, which means I'm going to be multiplying 3 times 2, which, of course, right here shows 6. And then that has a w times a w times a w. And that's the same amount multiplied by itself 3 times. So that would be w to the 3rd power, which is shown here. And so 6w3 is our final volume solution for this particular shape. So now let's zoom back out and let's talk about this. So let's put w as 1, right? If my width is 1 centimeter. So the w would be a 1. 1 to the 3rd power would be 1 times 1 times 1, which of course just equals 1. And then times 6, because we have the 6, and that's just going to be 6 cubic centimeters. All right, but now let's put a 2 in there. That would be 2 times 2 times 2. 8, very good. Times 6 is going to be 48 cubic centimeters. So you can see it takes a drastic change, huge change. Just by changing it 1 centimeter, we grew by 42 cubic centimeters in our volume. This is why three-dimensional shapes are so amazing and why trailers and sheds, things that hold materials, need to be done smartly so that you're buying the right amount of materials to cover how much space you need inside. So 3, let's try that one. Let's try 3. So plug that into our formula, 6W3. That would be 6 times 3 to the 3rd power, right? And I don't really even need these parentheses, because I'm going to do the parentheses first. I'm going to do the exponent first anyway in PEMDAS, because it's please excuse my dear Aunt Sally. So 3 to the 3rd power, that would be 3 times 3 times 3, right? And 3 times 3 times 3 is going to be 9 times 3, which is 27, right? So now we have 27 times 6. Right? 7 and 6 is going to be 42. 20 and 6 is going to be 120. 162. So wow, that one changed by even more, right? 162 is our cubic centimeters of that. And so this formula and using three-dimensional objects, finding out how they're connected and how they work together helps you better understand why exponents is different than just multiplication, because it's not just, you know, times 2 or times 3. It's times itself a certain number of times.
I hope this helps. If you need more information about exponents, just leave me a comment or message me on Schoology, and I can get you some more work. CommonCoreSheets.com has really good stuff for practicing that one-at-a-time practices. Also, Khan Academy is awesome. There's several different resources for you available. You know, I am by no means the only mathematical option you have. So please don't think that. Anyway, have yourself a wonderful day, and let's keep rocking that math.
I don't